Welcome to Chapter 3 video. This video covers sections 3, 4, 5, and 6. Section 3 covers the differentiation rule. Objectives: demonstrate the derivatives of a constant function, a function using the power rule, a constant multiplied by the independent variable, the natural exponential function, the product of functions using the product rule, the division of functions using the quotient rule, and functions to the second and higher order derivatives. Derivative of a constant function. If f has the constant value f of x equal to c, then d by dx of f equal to d by dx of the constant c equal to 0. The reason being, the function f of x equal to c is a function that's defined at y equal to c for all values of x, and that's like a straight horizontal line that's parallel to the x-axis, and horizontal lines have slope equal to 0. For that reason, their derivative equal to 0, because the derivative is a slope. Rule: this is the power rule, the general version of the power rule. If n is any real number, then d by dx of x to the power n equals to n x to the power n minus 1. For all x where the power x to the power n and x to the power n minus 1 are defined. The power rule. Let's prove that dx to the power n by dx equals to n x to the power n minus 1. Note, r chosen from n possibilities is same as NCR. For those of you who know NCR but not r chosen from n possibilities. Now let's get back to our proof. We want to prove that dx to the power n by dx equals to limit as h goes to 0 of x plus h to the power n minus x to the power n divided by h. And this will be equal to limit as h goes to 0. We have 0 chosen out of n possibilities, x to the power n, h to the power 0, plus 1 chosen out of n of x to the power n minus 1, h to the power 1, plus 2 chosen out of n, x to the power n minus 2, h square, plus all the way until n chosen out of n of x to the power 0, h to the power n. This ends the expansion of x plus h to the power n, and then we have to subtract from it x to the power n. It's clear that since n 0 chosen out of n is equal to 1 and 1 chosen out of n is equal to n, then the first and the last terms cancel one another. The first term is 0 chosen out of n, so that means this will lead us 0 chosen out of n is equal to 1. So that means we have x to the power n, and then h to the power 0 is equal to 1. So we have x to the power n, and then all the way the last term is negative x to the power n. So x to the power n minus x to the power n cancel each other. That's why we said here the first and the last term cancel one another. What are we left with? We're left with limit as h goes to 0, 1 chosen out of n, x to the power n minus 1, h to the power 1, plus 2 chosen out of n, x to the power n minus 2, h square, plus all the way until n chosen out of n, x to the power 0, h to the power n. Now, this is divided by h. If we look at the terms, we see the only term with h to the power 1 is the first term. From the second term on, h exponent will continue to increase until it gets to h to the power n. That means if we divide by h, what will happen? here is what's going to happen. First of all, we're going to go ahead and cancel some of them. Definitely, this is the only one. So if I want to cancel h to the power 1, this will cancel with it, h to the power 1. But then over here, this is going to be h, and then every one of them, this is going to be h sub n minus 1. So every term will contain h. When we take the limit as h goes to 0, then it's going to cancel every term. It's going to be cancelled all the way. Every term is going to be cancelled. The only term that will survive is the first term. The first term is 1 choose out of n of x to the power n minus 1. We just said that 1 choose out of n is equal to n. So since 1 choose out of n is equal to n, we're going to go ahead and plug in for n choose 1, this one. So it's going to be equal to n x to the power n minus 1, which is the result we're looking for, which is right here. Example 1. Differentiate the following powers of x. X to the power 3. So d by dx, x to the power 3 is equal to 3x to the power 2. Number C. D by dx of x to the power square root of 2 equal to square root of 2 x raised to the power square root of 2 minus 1. E. D by dx x to the power 4 over 3, negative 4 over 3. That's equal to negative 4 over 3 x to the power negative 7 over 3. If u is a differentiable function of x and c is a constant, then d by dx of c multiplied by u equal to c multiplied by du by dx. This rule can be proven using the product rule. Try to prove it using the product rule. Derivative sum rule. If u and v are differentiable functions of x, then the sum u plus v is differentiable at every point where u and v are both differentiable. At such points, the derivative of the sum equal to the sum of the derivatives. One more time, the derivative of the sum equal to the sum of the derivatives. Example 2. Take the derivative of the following functions. Number 1, y equal to 3x squared, and number 2, y equal to negative x. D by dy of 3x squared, 3 is a constant, x squared is the variable, so we take the constant outside and we'll do the derivative of the variable. So if 3 is outside, dx squared by dx is equal to 2x multiplied by 3 is 6x. The second problem is dy by dx equal to d by dx of negative x. So negative x, that means negative 1 multiplied by x. So we take negative 1 out, and then we do by dx by dx, and that's going to give us negative 1. Example 3. Find the derivative of the polynomial y equal to x to the power 3 plus 4 over 3 x squared minus 5x plus 1. dy by dx is equal to d by dx of x cubed plus d by dx of 4 over 3 x squared minus d by dx of 5x plus d by dx of 1. The result term by term. The first term will give us 3 and then x to the power 2. The second term will give us 8 divided by 3 multiplied by x. The third term will give us negative 5. And the last term will give us 0 because the last term is constant. Derivative of constant is equal to 0. Now, example number 4. Does the curve y equal to x to the power 4 minus 2x squared plus 2 have any horizontal tangents? If so, where? The derivative of the horizontal line equals to 0. Why? Because the horizontal line, its slope is equal to 0 and the derivative of the slope are the same. So because the derivative equals its slope, therefore dy by dx equal to d by dx of x to the power 4 minus d by dx of 2x squared plus d by dx of 2. And we can do the derivative, so there will be 4x to the power 3 minus 4x to the power 1 plus 0, which is equal to 4x to the power 3 minus 4x to the power 1. Since the derivative of a horizontal line equals 0, then we equate this equation 4x to the power 3 minus 4x equals 0. This implies we can divide by 4 before we do anything, so we'll be left with x cubed minus x, and then we take x outside, so it will be x squared minus 1. That's equal to 0, implies x equal to 0 and x equal to negative 1 and x equal to positive 1. 3 values. These are the points where the tangent is horizontal. This figure represents the problem that we just solved. The curve in example 4, which we just solved, and it is horizontal tangents. The horizontal tangents, as we said, at x equal to 0, this is x. When x is equal to 0, plug for x 0. Then we'll get what? 0 minus 0 plus 2, so y is equal to 2. And when x is equal to negative 1, you evaluate, you'll get y equal to 1. And when it is equal to positive 1, y will also be equal to 1. So these are the 3 values, and you can see that the curve will have a tangent that's equal to 0. That means horizontal for these 3 points, and that's the point that we wanted. Derivative of the natural exponential function d by dx of e to the power x is equal to e to the power x. This is very strange. This is one of the strange functions. The derivative of the function is the function itself. Example 5. Find an equation for a line that is tangent to the graph of y equal to e to the power x and goes through the origin. Assume the line is a tangent to the curve f of x equal to e to the x at x equal to a. Then the slope of the curve should be e to the power a, because the slope is the derivative of the function. Derivative of e to the x is e to the x, and we want the slope at the point a. We replace x by a, so the slope is going to be e to the power a according to the curve. Now let's take a look at the slope of this line. The slope of this line is the tan of this angle. The tan of this angle is e to the a divided by a. E to the a is the opposite, divided by a is the adjacent. So the slope according to the red line is e to the a divided by a. The slope according to the curve at this point is e to the a. So that is what we have. However, using the line, slope is e to the power a over a, and before we mentioned that the slope of the tangent according to the curve is e to the power a. The fact that e to the power a must be equal to e to the power a over a because they are the same slope implies that a must be equal to 1. That's why over here the book says the line through the origin is tangent to the graph of y equal to e to the x when a equals to 1. Now we will go ahead and discuss the derivative product rule. It says if u and v are differentiable at x, then so is their product, u multiplied by v, is also differentiable at x. If that is the case, then we can find the derivative of the product of u times v. That's going to be equal to u multiplied by the derivative of v plus v multiplied by the derivative of u. So we have to answer 2 questions. Number 1, find the derivative of a y equal to 1 over x multiplied by x squared plus e to the x. So we will take u to be equal to 1 over x. In that case, u prime will be equal to negative 1 over x squared. And then we take v to be x squared plus e to the x. This is v equal to x squared plus e to the x. And then we get the derivative of v as v prime. V prime will be equal to 2x plus e to the x. Now all we need to do is just plug in the values. So we have the derivative of the first, which is u, multiplied by the second, which is v, equal to, we keep u as it is, but we differentiate v. This is v. So we just differentiate this, will give us 2x plus e to the x, which is right here. And then plus, this is v, which is x squared plus e to the x, multiplied by u prime. And we know that u prime is equal to negative 1 over x squared. So we have v, and this is negative 1 over x squared, which is derivative of u. Then all we have to do is we have to take 1 over x inside this parenthesis. So 1 over x multiplied by 2x will give us 2, plus 1 over x multiplied by e to the x will give us e to the x divided by x. And then we have this negative sign. We can take it outside and we replace the plus. It will be minus over here. And then we take 1 over x squared inside, so we multiply it by x. 1 over x squared multiplied by x squared will give us 1, plus 1 over x squared multiplied by e to the x will give us e to the x divided by x squared. Now we can remove this parenthesis, so we'll have 2 plus e to the x divided by x minus 1, and then minus e to the x divided by x squared. We know that 2 subtract 1 from it, 2 minus 1 is going to give us 1. And then e to the x over x is common between these two. So we'll take e to the x over x as a factor. From this one we'll get 1, and from this one we'll get minus 1 over x. And that's pretty much the answer. Now let's take a look at part B. Part B is y equal to e to the 2x. So part B here, y equal to e to the 2x. E to the 2x is equal to e to the x multiplied by e to the x. So we'll take 1 as u and 1 as v. And then we have derivative of u dot v equal to u derivative of v plus v derivative of u. But we know that derivative of e to the x is e to the x. So this is u derivative of v plus v derivative of u, which will give us e to the 2x plus e to the 2x. That is 2 e to the 2x. And that's pretty much the answer for what we want. Next we have to do this example number 7. Example number 7 is as follows. Find the derivative of y equal to x squared plus 1 multiplied by x cubed plus 3. Now we could just go ahead and multiply these two. If we multiply them, we have x squared plus 1 multiplied by x cubed plus 3 is going to be equal to x to the power 5 plus 3x squared plus x cubed plus 3. And this is what we have here. Y equal to x to the power 5 plus 3x squared plus x cubed plus 3x. We get the derivative of each term. So derivative dy by dx equal derivative of the first term, which will give us 5x to the power 4. Derivative of the second term will give us 6x. Derivative of the third term will give us 3x squared. Derivative of the fourth term will give us 0. So we ignored it. So this is the derivative. Derivative quotient rule. If u and v are differentiable at x and v of x is not equal to 0, then the quotient u over v is differentiable at x and the derivative of the quotient u divided by v is equal to v derivative multiplied by derivative of u minus u multiplied by derivative of v over v squared. Now what we have is an example 8. Find the derivative of a y equal to t squared minus 1 divided by t cubed plus 1. We will take u equal to t squared minus 1, which is the numerator, and we do the derivative of u, it's going to give us 2t. We take v, which is the denominator, and v will put it equal to t to the power 3 plus 1, and then we do the derivative of v, dv by dt will give us 3t squared. Now that we have the formula, and these are all the variables, and these are the values of the variables, all we have to do is plug in the values of the variables where they're supposed to. So we will take a look at, therefore here d by dx of u over v equals to, this is v, and you can check it on the left, v is right here, v, and this is the derivative of u, and you can check it over here, this is derivative of u. So v multiplied by derivative of u minus u, this is u, you can check it right there, this is u, multiplied by derivative of v, and this is the derivative of v. So we have v derivative of u minus u derivative of v, and then we have to divide that by v squared, and we know that v is equal to t cubed plus 1, so v squared is t cubed plus 1 all square. Now this is the end of the first part. The second part, y equal to e to the negative x. So we put y equal to e to the negative x, and we take e to the x down, so it will be equal to 1 over e to the x. Now we will let u equal to 1, so derivative of u equal to 0 because 1 is a constant. And we will let v equal to e to the x, derivative of v is equal to e to the x because derivative of e to the x is e to the x. Therefore, if we apply the formula over here, we know that since we have du by dx equals 0, that means this term is equal to 0. So the first term will be equal to 0, which is right here. And then the second term is u multiplied by derivative of v. We have u is equal to 1, derivative of v is equal to e to the x, and that's why we have minus e to the x, divided by v squared. We have v equal to e to the x, so v squared will be equal to e to the 2x. So if you do the math here, I have minus e to the x divided by e to the 2x will give us minus e to the minus x. And that's it for this part. Example 9. Rather than using the quotient rule to find the derivative of y equal to x minus 1 multiplied by x squared minus 2x divided by x to the power 4, expand the numerator and divide by x to the power 4. Let's take a look at the function y equal to, and then we're going to have to multiply x by x squared. It's going to give us x to the power 3, and then x by negative 2x, it will give us negative 2x squared, and then negative 1 multiplied by x, it will give us minus x squared, and then finally negative 1 multiplied by negative 2x will give us positive 2x. Then when we divide this by x to the power 4 term by term, this is what we're going to get. The first term, which is x to the power 3, it will be minus 3x squared plus 2x divided by x to the power 4. Now we do the division. So this will be, the first term will give us x to the power negative 1 minus 3x to the power negative 2 plus x to the power negative 3. Therefore, the derivative dy by dx is equal to negative x to the power negative 2 plus 6x to the power negative 3 minus 3x to the power. Now we discuss second and higher order derivatives. Representation is f double prime of x equals to d2y by dx squared. This is equal to d by dx of dy by dx. It's also equal to dy prime by dx, or just for simplicity, y prime prime. Now we can generalize y n equal to d by dx of y n minus 1, which is equal to dn of y divided by dx n. Example number 10. Find the higher order derivatives of y equal to x cubed minus 3x squared plus 2. So let's get the equation first. So y equal to x cubed minus 3x squared plus 2. Y prime will be 3x squared minus 6x. Y prime prime will be equal to 6x minus 6. Y triple prime will be equal to 6. Y 4 primes is equal to 0. That's it. That ends this section 3.3. The next video will start from section 3.4. Section 3.4. The derivative as a rate of change. Objectives. The objectives of section 3.4 and 5 and 6 are as follows. To explain rate of change of a function at a specific point in its domain, derivatives of trigonometric functions, derivative using the chain rule, repeated use of the chain rule with power of function. Before we get into finding the rate of change of a circle's area with respect to diameter, we're just going to make a hypothetical situation. We assume that this slide is full of water, deep water, and we assume that a person threw a stone and the stone hit the water. The stone is heavy, so the stone will sink, but the impact will cause circles on the water. If you haven't seen it, just go ahead and throw a stone in the water. You will see circles, but the circle get bigger and bigger until the impact is equalized, and then it will stop. Let's take a look at what will happen. This is very important for engineering. It will be even in situations like when there is danger spreading, like this circle, then you have to figure out how much time it's needed to, for example, put off a fire or do something before the circle increases and includes, for example, homes or any civic place where it's going to damage it. We're not going to get into that one, but anyway, it's important, and we're going to go into the calculus part of it, which is calculating the rate of change. So here is the experiment that we're talking about. Here is the person, here is the stone. We're assuming still there is a lot of water that is deep here, and the person comes and throws the stone. So what will happen now? Upon impact, there will be a circle, and then the circle will continue to grow. The circle will continue to grow. Okay, so the circle will continue to grow, and all we need is to find out the rate at which the circle grow. Like, for example, if you have houses over here, and this happened to be a fire, and the fire started spreading in all directions, you want to know how much time this fire is going to reach people who live over here. If you have enough time, then you will do your best to put off the fire. Otherwise, you will evacuate the people from this place. Let's go ahead and see the mathematical part of it in the next slide. Now we're going to go ahead and go to example number 1. But before we do so, I just want to remind you that in the past, we used to do what is known as the definition of the derivative. And what we did is we looked at f of x, limit f of x as x goes to 0, for example, of whatever. Now we're not looking at f of x, we're looking at f prime of x, f prime of a specific value x0. So we're looking at this specific value. Why? Because we're looking at the instantaneous rate of change, not the rate of change, instantaneous rate of change of f with respect to x at x0 as specific time. It's just like when you look at the speed at the odometer. When you look at that speed, that's that speed at that specific time. So that's what we're trying to do now. And we assume that the limit exists. So to apply this rule, let's take a look at example 1. Example 1 is about the area of a circle, okay, which is related to its diameter by this equation. That means the area is going to be equal to pi over 4 multiplied by d square. Pi over 4 is constant, so it's not going to change, but changes in d is going to change the area. If d grows larger, then the area will grow larger. So that's why to find the area, to find the rate of change also, we have to do the derivative of the area with respect to the diameter. So d of a divided by d of d equals to d by dt of pi over 4 d square. And when we do the derivative, it's just that this is a constant pi over 4, so we keep pi over 4 and we do the derivative of capital D square, and that's going to give us 2d, but we have 4, so the 2d, we cancel 2 with 2 from the 4, and we will get pi over 2d. We're asked to find how fast the area change with respect to the diameter when the diameter is 10 meters. So we replace d by 10 meters, and then of course the 10 divided by 2 is going to give us 5, so that is 5 pi units. 5 pi units is the answer. So the units is meters, for example, so 5 pi meters. That's it for this example. Now, we know from section 2.1 that average rate of change in a position function gives the average velocity. If we need to find the instant velocity at a specific time, we need to find the instant rate of change of the position function at that specific. Section 3.5, derivative of trigonometric functions. The derivative of the sine function is cosine. So we can just say d by dx of sine x is equal to cosine x. Derivative of cosine x is equal to negative sine x. Derivative of tan x is equal to sec square x. Derivative of cotan x is negative cosec square x. Derivative of sec x equal to sec x tan x, and derivative of cosec of x equal to negative cosec of x cot of x. Example number 1. We find derivatives of the sine function involving differences, products, and quotients. To start with, let's go ahead and get with problem number A. Y equal to x squared minus sine x. To get the derivative of y, we do the derivative of x squared, and then we do the derivative of sine x. So y prime equal to 2x, which is the derivative of x squared, and then cosine x, which is the derivative of sine x. And this is an example of difference. So this is example of the difference. B, y equal to e to the x sine x. We set u to be equal to e to the x and v to be equal to sine x. So u prime will be equal to e to the x and v prime will be equal to cosine x. And this is the product rule. So y prime, the derivative, equal to u v prime plus u prime v. And that's equal to u is equal to e to the x, and then v prime is equal to cosine x, so e to the x cosine x, plus we have u prime, which is e to the x, and v is sine x, so e to the x sine x. We could just take e to the x as a factor, and then we'll have sine x plus cosine x. And this is an example of product. Last example is obviously this is an example for the quotient. So we can just say we're going to set sine x to be equal to u and x to be equal to v. So u prime will be cosine x and v prime will be equals to 1. Now we use the rule y prime equal to v u prime minus u v prime divided by v square. So our v is equal to x. So this x, our u prime is equal to cosine. So x cosine x minus u, which is equal to sine x, and multiplied by v prime, which is equal to 1. So just minus sine x divided by v prime. V is equal to x, so v prime is equal to x squared. And that's an example of the quotient. Example 2. Example 2 is about a cosine involved with other functions. For instance, part A, it has the cosine involved with an exponential function. Part B, it has a cosine involved with sine, so this is pure trigonometric. And part C is also cosine involved with sine, so this is also trigonometric. So I'm going to go ahead and do the combination of the exponential and trigonometric and leave the other two, B and C, for you as homework. So let's get going with the first one. So we want the derivative of y, which we represented here by y prime equals to derivative of the first term, which is d by dx of 5e to the x, plus derivative of the second term, which is d by dx of cosine x. Now d by dx of 5e to the power x is going to give us 5e to the power x. And then we have plus derivative of cosine x is equal to minus sine x. That's why the sign changed to minus here, and we have sine x. So that's the first one, and please do the other two as exercises. Section 6. Derivative of a composite function. We have y equal to 3x squared plus 1 all square. Let u equal to 3x squared plus 1. Then du by dx equal to 6x. And now we will set y equal to u squared, because we have u equal to 3x squared plus 1. So we will replace 3x squared plus 1 by u. And that will give us y equal to u squared. Implies dy by du is equal to 2u. Now we will use dy by dx equal to dy by du multiplied by du by dx. We know we have dy by du equal to 2u. So we have 2u first, and then multiplied by du by dx. We already have du by dx equal to 6x. So it's 2u multiplied by 6x. Now we'll go ahead and put the value of u back. Remember, we said let u equal to 3x squared plus 1. So we replace u by the original value, which is 3x squared plus 1. And then 6x will remain the same. So in the end, we will multiply 6x by 2, and we will get 12x multiplied by 3x squared plus 1. We've already gone through the rate of change of a function at specific point. We have also discussed the composite functions. Now we will be discussing the composite functions as rate of change. So let's take a look at the combination of the rate of change and composite functions. We have this function in purple, that's the graph for it. The function has its domain x, and its range is going to be at this point, where its range contains all the g of x's. So we want to take a look at the rate of change of the function f at g of x, and then we want to take the rate of change of g of x at x. So that is the purple one. And then let's go back to the two-step, which achieves the same thing, g and f. So we will look at the rate of change of g at x, and over here we take g of x and we find rate of change of f at g of x. and that will give us the same answer. So we have here rate of changes multiply the derivative of f composed with g at x is the derivative of f at g of x times the derivative of g at x. That's just basic summary. We have an important theorem about this composite function. It's called the chain rule, theorem number 2. If f of u is differentiable at the point u equal to g of x, and g of x is differentiable at the point x, then the composite function f circle g operating on x is equal to f operating on g of x is differentiable at x, and the composite function f circle g prime, that means the derivative of this at x, is equal to the rate of change of f prime at g of x and then rate of change of g of x at x. In Leibniz notation, if y equal to f of u and u equal to g of x, then we could have dy by dx equal to dy by du multiplied by du by dx, where dy by du is evaluated at u equal to g of x. When we take some examples, it's going to be clear. Example 2 is about an object that is moving and its position is given by an equation that depends on t greater than or equal to 0, and the equation is x of t is equal to cosine of t squared plus 1. We want to find the velocity of the object as a function of t, and to do so we will let the argument of cosine, which is t squared plus 1, we will let u equal to t squared plus 1. So in that case, du by dt is equal to 2t, and cosine of t squared plus 1, because we said let u equal to t plus squared plus 1. If u is equal to t squared plus 1, then cosine t squared plus 1 is equal to cosine u. And we know cosine t plus 1 is equal to x of t. So x of t, which is equal to cosine t squared plus 1, will also be equal to cosine u. So if x of t is equal to cosine u, then we can do dx by du is equal to negative sine u. Now that we have all of these, all we need now is to replace dx by dt, which is dx by dt, derivative of this. We replace it by dx by du multiplied by du by dt. I'm going to go ahead and change the positions of these two. I'm going to put du by dt first multiplied by dx by du. Now we have the first one, du by dt. We already said that is equal to 2t, so we have 2t in place of du by dt, and then we have to multiply that by dx by du. But then dx by du, we found it to be equal to negative sine u. So we're going to go ahead and multiply. Instead of dx by du, we put negative sine u. So we have 2t multiplied by negative sine u, that's equal to negative 2t multiplied by sine, and instead of u, we're going to go ahead and replace it by t squared plus 1. And that's going to give us the answer. Example number 3. This deals with the outside-inside rule of differentiation. So we have to differentiate sine of x squared plus e to the x with respect to x. So let us set this function as y equal to sine of x squared e to the x. We let u equal to x squared plus e to the x. Then it follows that du by dx is equal to 2x plus e to the x. And we can also conclude that y equal to sine u. Why? Because we set u to be equal to x squared plus e to the x, and we have here y equal to sine x squared plus e to the x, so we can replace this by u. So y equal to sine u, which is what we have over here. Now from y equal to sine u, we can find the derivative. So dy by du equal to cosine u, derivative of y. So derivative of y with respect to u is equal to cosine u. Then we can use the rule, where the rule states dy by dx equals to differentiation of the outside and then differentiation of the inside. Differentiation of the outside is the cosine u, because we are differentiating with respect to y. So y is equal to sine u, differentiation of y is cosine u. So we have cosine u over here. And then dy by du multiplied by du by dx. Du by dx is differentiation of what is inside. And the inside is x squared plus e to the x, which we call the du. So we can see that du by dx is equal to 2x plus e to the x. So we just replace du by dx by 2x plus e to the x. Now we have to reset back the value of the argument of the cosine. From u we put the equal. What is equal? U is equal to x squared plus e to the x. So we just go ahead and replace u by cosine and inside x squared plus e to the x. So we replace u by x squared e to the x. And this is pretty much the answer that we're supposed to. One more time. This value is the differentiation of the inside, and this value is a differentiation of the outside. And if you can see that cosine here is working on x squared plus e to the x, and you can see that on this left hand side is the derivative of the argument of the cosine. That's it for this one. Let's take a look at another example. Number 4. Example number 4 is about derivative of y equals to e to the power cosine x, which is a combination of logarithmic and trigonometric. So y equal to e to the cosine x. It looks like it's intimidating, but it's not really. Let's go ahead and start denoting d by dx of e to the power cosine x. We first let u equal to cosine x. Then the derivative of u with respect to x will be du by dx equal to derivative of the right hand side, which is negative sine x. We also know that y equal to e to the cosine x, and we replace cosine x by u. So we can say y equal to e to the u, which is right here, y equal to e to the u. Now we get the derivative of y with respect to u on the right hand side and the left hand side. So dy by du is equal to e to the power u, because the derivative of e to the power u is e to the power u. Now we can use the differentiation rule for the outside inside. So dy by dx equal derivative of the outside, which is dy by du, multiplied by derivative of the inside, which is du by dx. Now we could replace dy by du by its equivalent. We said dy by du is equal to e to the power u. So we're going to replace the left hand side of the multiplication by e to the power u. The right hand side of the multiplication, we have du by dx equal to negative sine x. So we replace this by its value. So we have e to the power u multiplied by negative sine x. And we could just go ahead and put back the value of u. The value of u is cosine x. So we could just go ahead, instead of e to the power u, we just put e to the power cosine x. And then the negative outside, we'll take it outside. So it's negative e to the power cosine x multiplied by sine x. That's the result of this part. Now we have to prove this part, so we're going to use this result also. So just watch it. We let u equal to cosine x. Then d by dx of e to the cosine x is equal to d by dx of e to the u, because we said u equal to cosine x over here. U equal to cosine x. I repeat it over here for convenience. So we have d by dx of e to the u, which is the left hand side. So let's keep in mind the left hand side. Let's try to derive the right hand side. We also proved that d by dx of e to the cosine x equal to e to the cosine x multiplied by negative sine x, which is a proof that this derivative is equal to this value. So we also proved that d by dx of e to the cosine x equal to the e to the cosine x multiplied by negative sine x. Let's get this cosine x changed to u. Cosine x is equal to u. So we'll change cosine x to u and put it on the right hand side here. So it's e to the u, and we know that negative sine x is nothing but the derivative of du by dx. So we replace e to the cosine x by e to the power u. We replace negative sine x by du by dx. So we have e to the power u dot du by dx. And here we go. This is d by dx of e to the power u equal to e to the power u multiplied by du by dx, which proves this value. And of course, what we use is the inside, u equal to cosine x. We found du by dx equal to negative sine x. And that's why we replaced du by dx over here instead of. That's it for this side. And if you have any questions, please feel happy to send them to me. Let's take a look at more questions to answer, more exercises. We're going to be doing something that's a little bit different than what we've done in the last slide. This is repeated use of the chain rule that we used before. So we're going to use the chain of the chain. Now let's go ahead and see what we meant by that. We sometimes have to use the chain rule twice or more times to find a derivative. Over here, I hope it's not going to be more than twice. Let's see. Example 5. Find the derivative of g of t equal to tan of 5 minus sine 2t. First assumption. Let u equal to 5 minus sine 2t. It follows that g is equal to tan u, because we just said we want u to be replacing 5 minus sine 2t. So g of t will be equal to tan. We'll replace this by u. So it will be tan u. And that's what we have here. G equal to tan u. And then we have to take the derivative of g with respect to u. So dg by du is equal to sec square of u. This is the first assumption. The second assumption that we will let v equal to 2t. If that's the case, then it follows that u equal to 5 minus sine of, instead of 2t, we're going to put v over it. If we do so, then we can take the derivative of dv by dt, and here is v as a function of t. So dv by dt is equal to 2. If we did the derivative of the left and the right, we'll get 2. Now we could take dv by now we will do du by dv, the derivative of u with respect to v. But we're not going to use this, because this u is a function of t. We have to use this u. This u is a function of v. So du by dv equal to derivative of the left hand side, and of course derivative of the right hand side, the 5 will be equal to 0, and then negative will remain. Sine v will give us cosine v. So negative remained and cosine v. Du by dv equal to negative cosine v. Now it's high time that we do the derivative using the repeated chain. So dg by dt is equal to dg by du multiplied by du by dv multiplied by dv by dt. We have to just do plugging the value of this. We know dg by du equal to what? Equal to sec square u. So we're going to plug in sec square u here. The middle we have du by dv. We know what du by dv is because it's right there. Du by dv is equal to negative cosine v. So we stick in here negative cosine v. The right hand side dv by dt, we know what it is because dv by dt is equal to 2, so we put 2 there. Now we will make some rearrangement. So the 2, we're going to take it all the way to the left because it's just multiplied by the result of multiplying these two. So we have 2 here, and then we have sec square of 5 minus sine v, because u over here it's equal to 5 minus sine v. So we just placed, instead of u, we said put 5 minus sine v, and then this is multiplied by negative cosine v. So we're going to replace v by 2t because we said v is equal to 2t. So negative cosine v is now negative cosine 2t. Now we have to replace v over here also. So this line is going to be equal to 2, and then sec square of 5 minus sine, instead of v, we'll put 2t because v is equal to 2t. And then that's multiplied by negative cosine of 2t. And that ends the proof. And it is really nice. It's just a little bit more time than the usual ones that we've been doing. Repeated will take a little bit more time. You can see repetition is going 3 levels. Before we just did 2 levels, but it's nice. You will be needing it in some situations. Okay, that's it for example 5. Let's take a look at the next. Example 6 is like a shortcut of the rule that we just went through. And you can see that this is the chain rule with powers of a function. So we have d by dx of u to the power n equal to n, and then u to the power n minus 1, and then the inside derivative du by dx. So let's try to apply it here. We have d by dx of 5x cubed minus x to the power 4 all to the power 7 equal to 7, and then we keep whatever inside the same, and then we subtract from 7 1. So it's just like we're dealing with this as a single variable. So we said 7, whatever this one is, to the power 7 minus 1, which is 6, and then we do the derivative of whatever inside. So that will give us 7, and then 5 to x to the power 3 minus x to the power 4 all to the power 6 multiplied by the derivative of the inside, which is going to be 3 times 5, which is 15, x to the power 2 minus 4 x to the power 3. This is a derivative of the inside. This is a derivative of the outside. Let's go ahead and repeat it on b. We have b, the derivative is d by dx of 1 over 3x minus 2. This is equal to d by dx of 3x minus 2 all to the power negative 1. Now we can do also the same derivative. So we take the exponent down, so it will be minus, and then we differentiate the whole, which will give us 3x minus 2 to the power negative 2. And then we have to multiply it by the derivative of the inside, which is 3. And that will give us negative 3 divided by 3x